In this video, I'd like to explore solving literal equations, and when we use the word literal, we're talking about equations that often have more than one variable, and in this video specifically, I want to explore further solving for a variable in the denominator. So first, if we review how to solve a literal equation, we remember that we can solve literal equations in the exact same way as the equations we have solved up to this point that only had one variable. So first we're going to apply inverse operations in the opposite, that's the key word here, opposite order of the order of operations, or in other words, our PEMDAS. And we're going to do this until the variable is by itself, or we often use the word isolated, or alone. Now, the one thing that we do note is different about solving a literal equation versus the other equations in the past that had a single type of variable is that because we have more variables, we're going to have less like terms. So ultimately, as we simplify, we just won't be able to simplify the equation as far, and we'll have a more complex answer. So as a review, let's look at this first problem we're asked to solve for x. The first thing we want to do is always identify what the other operations are around our key variable x, and in what order we need to identify and deal with those. So first, I have this a and the x, and since there's no operation between those, I know that this is multiplication. Secondly, I have this addition between the x and the 2y, and by the inverse order of operations, in other words, going by the order of operations backwards, I know that before multiplication, I need to deal with the addition first. So, as we solve this equation, the first thing I should recognize is that I need to deal with this addition of 2y, trying to get the 2y on the other side of the equation. So I'm going to apply the inverse operation, and I'm going to subtract 2y from both sides of the equation. Now as we do this, we note that z and 2y on this right-hand side of the equation, so over here the z and the 2y, these are not like terms because they are different variables. So I'm not going to be able to combine them, but that doesn't mean I can't rewrite the equation. So I can do this now. On the left-hand side of the equation, I'm left with our ax term. The 2y and the negative 2y add to 0 by definition of inverses. And we're left with equals to, I'm just going to write all the operations, z minus a2y. And again, I'm not combining those terms because they're not like terms. But I can see that I now have less things to do with on this left side of the equation, and we're getting closer and closer to getting x alone and by itself. So now at this point, I have to deal with the second operation. Because there's nothing occurring between the a and the x, I assume it's multiplication. And this means that I have to divide both sides. Now I'm multiplying by x, or rather multiplying a and x. So the inverse of that multiplication is going to be division, and I'm going to divide by a. Now the key thing here though is I'm dividing the entire side of the equation by a. So I have to divide also the entire side of the right-hand equation. I'm not just dividing z, I'm not just dividing 2y, I'm dividing the entire side of the equation. This can be a little tricky. Now on the left-hand side, a divided by a, I can write this out, a divided by a is just equal to 1. So technically I don't actually need to write a divided by a since these inverse operations just cancel. So all we're really left with then is the x equal to, and again I'm not simplifying because I don't have any like terms. So I'm just going to write z minus 2y all divided by a. Notice all three of my variables are different, so I really can't do anything about this. So this is ultimately our simplified solution for x because we can't combine any of those like terms. Here's a second example, and we're asked to solve for x once again, and I have three different variables. I have b, d, and e all being on that left side of the equation performing operations on x. So I need to do something to get rid of those. So again, I'm going to talk about the operations that are occurring. I can see that the b is being multiplied by x. I can see that d is dividing x. and I can see that e is then being added to this whole fraction. So by the inverse order of operations, the first thing I should deal with is the addition. We've talked about this quite a bit, how I need to solve in the opposite order of operations. Just as a reminder, I can write the order of operations up here, PEMDAS. And normally, when we're simplifying, we go left to right, but because we're not simplifying, we're solving, we're going to go right to left, the opposite of the order of operations, and I can see that the first thing I should deal with is our addition and subtraction. So I'm going to deal with this. I notice that I have this addition of e. I'm going to subtract that e from both sides. And this is going to leave me then with plus e and negative e, add to 0. So nothing but bx over d equals, and on the left-hand side, I can't combine f and e because they're different terms. So I'm just going to write f minus e. Now I'm going to continue here. Whenever I have a fraction, I've talked about in the past how there's an implied set of parentheses on the top of that fraction. So even though I have multiplication and division, the last thing I need to deal with is what's in the top of this fraction. So I'm actually going to go ahead and deal with the division by d, and I deal with that division by multiplying both the left-hand side of the equation by d, which means I also have to multiply the right-hand side of the equation by d. So again, now we're dealing with the multiplication before we deal with the final thing, the parentheses that we see in the top of that fraction. So multiplying through, I'm going to end up with d times b over x divided by d. Again, we notice that the multiplication and the division by d divide to 1, or in other words, they cancel. So by definition of inverses, I'm only left with bx over here. Now over here, as I multiply, I put the parentheses reminding me to multiply the entire equation, which means I have to distribute to both terms. But again, I can't combine, so I'm just going to write out what we get here. D is being multiplied by f, minus d is being multiplied by e. And now we're almost done. There's only one more operation to deal with, which is this b. Because it's being multiplied, I'm going to do the inverse operation, which is division. So dividing by b, again, multiplication and division for the same variable, divide and cancel. So all I'm left with now, and if we come over here for our final solution, on the left-hand side is x equal to, and again, I can't simplify it all because they're all different variables, so I'm just going to write df minus de all over b as our final solution. Now I want to explore further the idea of solving for a variable in the denominator, or in other words, in the bottom of a fraction. And the first thing we note is that if we need to solve for a variable in the denominator, the first step is going to be to move the variable out of the denominator. So to move the variable out of the denominator. And remember that the denominator is the bottom of the fraction. So denominator. And the idea here is that it's very hard to solve for that fraction. Even if I get the variable all by itself, if it's in the bottom, it's going to be 1 over that variable. So think about like if you're trying to get 2 by itself, 2 in the denominator is actually 1/2, not 2. So in order to solve for the true variable, we have to first move that variable out of the denominator. Now to do this, it's actually pretty simple. We can do this by multiplying both sides of the equation by exactly the denominator. And this is all going back to the properties of inverse functions. The whole bottom of a denominator is dividing denominator. So in order to cancel that division, we just have to perform the exact same multiplication, and we should just be left with the numerator. So let's explore this in action. As a real simple example, I like to start with one that we even know what x should be just by looking at it. Since x is dividing 8, I should be able to just look here and see that 8 divided by 2 would give me 4. So we can kind of use this as a check to make sure the process we're using actually makes sense and works. Now, in order to solve this equation and more complicated equations, what I recognize is I have this variable x in the denominator. In order to solve any complex equation where x is in the denominator, the first thing we need to do is get x out of the denominator. And my argument is that if I simply multiply both sides of this equation by x, or in other words, x over 1, if that makes it a little bit easier for you to think about, I'm going to be able to actually solve for this more simply. So first, on the left-hand side of the equation, I have x times 4. These are not like terms, so I'm just simply going to call this 4x equal to, now on the right-hand side, this gets a little tricky. I have x being multiplied right here and x being divided. By the definition of inverses, I hope that these are just going to cancel each other. This is a little weird because they're now actually variables, but I can prove this by writing it a little bit differently. This is the exact same thing as if I wrote 8 over 1, or in other words, 8 times x over x. I can see in both cases I still have 1 and x being multiplied in the denominator, and then in the top I have 8 and x being multiplied together as well. Just like I see happening up here, x and 1 being multiplied in the denominator, 8 and x being multiplied in the numerator. The order of which is happening does not matter. So this is equivalent, but we can see really clearly here that x over x is just going to divide to 1, or in other words, I'm just left with 4x equals 8. And I can see I've actually accomplished my goal then by multiplying both sides by the denominator. I can see that x is now out of the denominator, and now we can simply solve by applying the inverse of multiplication, which is division, dividing both sides by 4. 4 over 4 divides to 1, and I'm left with x equals 8 over 4, or in other words, 2, just like we knew the answer would be. If we try another example, a little bit less obvious, I don't really know what I need to divide 7 by to get 4, because this is not going to be an integer answer. So we're going to have to work a little bit harder, but it's the same process. I notice that I have a variable in the denominator, and I want to get rid of that variable in the denominator. So I'm going to multiply both sides by x, or in other words, x over 1. Because I'm multiplying and dividing by x, these are going to divide to 1, and on the left-hand side of this equation, if I separate them, I'm going to be left with simply 7 equal to 4 times x. Now that x is out of the denominator, I can simply apply the division of 4 to both sides of the equation. Again, inverse. 4 is being multiplied and divided, so it divides to 1. And I'm left with the answer that 7 over 4 is equal to x. This is a less obvious solution, but we can see we can solve for these less obvious solutions in the exact same manner. I think a little bit more tricky this time. I'm still asked to solve for x, which I notice is still down here in the denominator, but now I'm no longer using numbers anymore, and we have nothing but pure variables. I still want to see, though, that we can still use this same process. So to get x out of the denominator, I'm going to multiply both sides by the denominator, which is x. Or in other words, again, I'm going to multiply by x over 1, or in other words, x on both sides of the equation. I can rewrite it again to be clear, but we notice that the x over x times the a over 1, which is what that original multiplication is equivalent to, is just going to divide to 1 because this term x over x is simply equivalent to 1. On the right-hand side of the equation, I know that I still have c times x. I can't combine these because these are different variables, but I at least notice that I'm on the right track here. So if I write this a little bit more simplified, this is now a equals c times x. Now I still want to solve for x, and I notice that I have multiplication here between the c and the x. To deal with this multiplication, I'm going to apply the inverse of multiplication, which is division, and I'm going to divide by the c that we're multiplying by. By the definition of inverses, c divided by c is going to divide to 1. So I'm left with my final answer, which is that a over c is equal to x. Here we have one more example, and I'm asking you to solve for a. And we notice that a is in the denominator, so again our first step should be to get a out of the denominator. To do this, I need to multiply both sides by this denominator. And notice I am multiplying the entire side, and I'm indicating this by putting parentheses around both sides of the equation. So I'm multiplying both sides by the denominator, a. So by definition, and here's where knowing that definition really comes in handy in these more difficult problems, multiplying and dividing by a are going to divide to 1. We can write this out by seeing that this is really a over a times x plus 4 all over 1. This is the same thing. I can still see I have 1 and a being multiplied in the denominators. So I can see that's equivalent. And if I look in the numerators, I can see that I have a times x plus 4 and a times x plus 4. So I haven't changed it, but now I can clearly see that the a over a here is just going to divide and become 1, which means we don't need this term anymore. This is equal to, on the other side of the equation, c times a, which I can't simplify because I don't know what those terms c or a are going to combine to, since they're different terms. So at this point I need to solve for a. I can rewrite it. I don't need that plus over 1. So I can just write this as x plus 4 equals c times a. To isolate the a, I simply need to divide both sides, and this is key, both sides of the equation by a, so not just the x, not just the 4, but both terms here on the left-hand side. By definition of inverses, a divided by a divides to 1, and I'm left with the answer x plus 4 over a equal to c, and we notice that I can't simplify anymore because none of these are going to be like terms. For the rest of your homework, I have 2 problems I'd like you to try on your own, and then also we have the worksheet reviewing more solving little equations that we went over in class.